All right, back again. So, just as the divergence of the magnetic field B equals 0 allows us to express B as the curl of a vector potential, i.e. B equal the curl of A, and we also know that the divergence of A, the vector potential, equals 0 permits us to write A itself as the curl of a, quote, higher potential. All right, so we get A written in terms of the curl of W. Okay, and if this pattern continues, we will find ourselves in an infinite loop of vector potential to curl, vector potential to curl. So part A wants us to know, find the general formula for W as an integral over B, which holds when B goes to 0 at infinity. Part B, determine W for the case of the uniform magnetic field B. C, find W inside and outside an infinite solenoid. All right, let's tackle it. For part A, we use the construction that divergence of B equals 0 and the curl of B equal mu naught J, with the divergence of A equals 0 and the curl of A equal B. So we chug that through and we see that we get A, which is can be expressed in terms of B, ultimately gets refined down to mu naught over 4 pi integral J over script R d tau. And similarly, if we shifted the things down and replace B with A and so forth, and A with W, we get that W equal 1 over 4 pi. B is the next thing there, script R over d tau. All right, that's kind of messy, but I can understand the analogy here. B, we got W will be proportional and to two factors of R, since differentiating twice must recover B. So R squared, derivative gives you R, derivative gives you B, or constant again. All right, so I'll try something of the form W equals alpha R dot B plus beta R squared B, which is the combinations, and see if I can pick up the constants alpha and beta in such a way that we know that the divergence of W equals 0 and the curl of W equals A. Fair enough. We got a lot of work ahead of us as far as the algebra is concerned. So if we take the divergence of W, we see that we have a product rule here inside the different vectors. I tried color coordinating this, and you'll see why in a second. So the first one, blue, is just a divergence of the position vector, which yields 3. Pretty straightforward computation there. Now the purple has to be expanded again into another product rule, this time with 4 parts. What we need to remember here is that B is a constant field, so any derivatives of B go to 0. Okay, so that's why in the original divergence equations we have del dot B equals 0. That's color-coded to red. The curl of B goes to 0 because the partials will cancel anything out. And we have R dot del, which again applies the derivative to the B field, and that goes to 0. Okay, and we remember that just from an interpretation of del cross R, that goes to 0 because the derivatives cancel out any components, or the evaluating of the derivatives cancel out any components. All right, so we really this product rule expands to del, or the gradient of R dot B, and it's equal to B dot del applied to R, which we see here just comes out through the computation to be B itself. Pretty clever, pretty nice. Now we know that del, or the gradient of R squared, yields the 2R vector. Now we can go back and substitute all these things in, and we see that we have the divergence of W is equal to alpha R dot B times 3 plus R dot B, and then we see we have plus beta, the R squared times 0 term, and then plus B dotted with 2R. Now we see we have everything written in terms of some factor of R dot B. Okay, so we can factor out the R dot B product, and we're left with coefficients of 4 alpha plus 2 beta. And if we're trying to find where this divergence of W equals 0, that will only happen where the coefficients equal 0, i.e. 2 alpha plus beta equals 0. Good to go there. But we also know that the curl of W is equal to the potential A, which again, with proper cancellations of things like the curl of R and derivatives of B go to 0, we can see here that from a previous problem that the potential A could be written in terms of the position vector across the magnetic field. And so we have a coefficient to set these things equal to each other. We see that the negative signs from the curl cancel, and we are left with alpha minus 2 beta equal 1/2. And then substituting in the results from the divergence, i.e. Beta equals negative 2 alpha, we can solve for alpha and then resubstitute in and solve for beta. And we see that the coefficient that we need is our 1/10 for alpha and negative 1/5 for beta. Plug them in and we get a potential W of the form 1/10 bracket R comma or R parentheses times the dot product of R and B minus 2R squared B. So although you kind of have an intuitive sense of how to set this up, and we have seen other problems where we have this R times the dot product, like the dipole expressions, now we see how we can put that together to formulate another, quote, higher potential. Okay. Now we see a diagram of the solenoid with some Amperian loop on it, which we'll use for the next part. So for part C, we have that del, or the curl of W, equals A. So if we integrate, we get the integral of the curl of W times dA, which is equal to the area, or the A vector dotted with dA. And then we could use the Stokes' theorem to put that in terms of a closed integral, or the surface integral, or a line integral, of W dot dL. Again, that equals to the integral of A dot dA. So if we integrate around the Amperian loop shown, taking W to point parallel to the axis and choosing W to equal 0 on the axis, we get negative WL equal the integral from 0 to S of, well, we know what that is, mu naught Ni over 2 L S bar ds bar. Again, plug it through, evaluate it, and we get W equals negative mu naught Ni S squared over 4 Z hat for inside of the solenoid. For outside, we have another expression where we need to take into account what we just found and add in an additional part for the Amperian loop, which gives us this natural log. Again, once you simplify it through and do all the fun stuff there, we see that we have W equals negative mu naught Ni R squared over 4 times 1 plus 2 ln S over R, Z hat direction for, again, S greater than R, which is outside. A little bit messy, but a lot of fun to see come together.